Great. Yeah. Thanks for the kind introduction. And I'm going to be talking about some of our work on simulation, which is very much in line with what we just had from the first talk. So um, I had the great fortune of working with an amazing team on this project. It's a very large team. So this is everyone involved. And the problem that we tackled is just that benchmarking autonomous vehicles is really hard. There's been a lot of skepticism, at least like from people I've talked to, regarding whether we have actually made real progress in the last year or so, because there has been a lot of hype and interest in end-to-end autonomous driving systems. There have been a lot of new research papers in this area, but it's really hard to compare these different papers and see if the performance is actually improved. So I want to illustrate this with a very simple example, which is based on like how benchmarking is done currently in a majority of the recent literature. So in this situation, you're like slowing down, approaching a red light, and I've projected three different possible future trajectories in three colors onto the image. And I think that most people would agree that the green trajectory here looks the most sensible, but it turns out that if you measure average displacement errors, which are the primary component of most evaluations these days on end-to-end self-driving methods, the red trajectory, which is veering off and crashing into this van, gets a better score than the green trajectory. It has a lower displacement error. And this is because the human driver who recorded this scenario in the data set actually slows down at a different frame compared to this model output, which is the green line. So if you take a different but correct approach to tackle a particular scenario, you can end up with a higher displacement error, even though this is like perfectly acceptable driving behavior. And this is not the only problem. There's like a great paper, which I believe is at CVPR, so definitely check it out in the paper sessions later, where this team discovered that the data set, which is most predominantly used in research on end-to-end driving, called NewScenes, has a lot of data which can simply be summarized as driving straight at nearly a constant velocity. So there's this heat map, which shows the distribution of trajectories given the ego vehicle placed at the top here. And 75% of the data kind of just goes straight. This leads to weird things in the results people have observed on this benchmark, such as I've plotted here a subset of papers that have been released on end-to-end driving between the end of 2022 and right now, so like in the last 2 years. And you have this set of different colors and different shapes in this plot. And it's so confusing because here all the shapes refer to different evaluation methodologies. Different papers kind of change the way the ground truth is calculated, change the way averaging is done, change which frames are sampled in the evaluation, leading to like a lot of inconsistent protocols. And there's also just a lot of different methods that came out. And surprisingly, like based on this displacement error metric where lower is better, a very naive type of model, which is called like a blind agent, which does no perception. So it just takes in the historical states and driver intention into a tiny MLP, can actually perform very competitively to most principled end-to-end driving methods that came out later on this particular benchmark. So it's not clear like how much progress was made with all of these newer methods, if they are like relying heavily on just this past trajectory input, or if they're actually doing something meaningful. So with all of this in mind, I want to quickly touch upon like simulation. So we had this like great talk just now about how you can benchmark in simulation. And it is true that simulation is more principled, but simulation does have its own issues as well. There are limited open source options, like Carla was mentioned as like the most popular and standardized one in the literature. But the problems that you get when working on Carla are that there's going to be a lot of domain gaps. The data is still not extremely realistic. The evaluation or running these simulations is actually very compute hungry because you need to render sensor data, which typically needs a lot of GPUs, and you need to benchmark these driving agents by doing a lot of driving, so several hundreds or thousands of kilometers, which eats up a lot of compute. And another subtle problem is that you have really huge variance in results reported on simulation-based benchmarks. So in Carla, which our group works on a lot, on a scale of 1 to 100 where the metrics lie, if you simply retrain your model, sometimes your score changes by 20 or 30 points. And not all papers train 3 or 5 seeds of each model they have in their paper, because this just further balloons up the amount of compute you need to do to actually make meaningful research in the simulators. So we have the situation where there's no ideal path for quickly and correctly benchmarking end-to-end driving algorithms, but there's still a huge community that's very interested in it. And this is sort of the hole we wanted to fill with this project. So the key idea of this particular method, which I'm going to talk about today, is something we call non-reactive simulation. And to simplify this is essentially bypassing all the challenges of simulation and making a very minimalistic simulator that can lie as a sort of middle ground between the very unprincipled displacement error based evaluation that we have out there, which is convenient, but kind of gives no signal as to whether your models are actually improving. And the more principled but very compute hungry simulator-based evaluation on Carlo or such. So this is going to be a middle ground of sorts between these two things. So what do I mean when I say we bypass the challenges of simulation? So if you think about it, there are two main challenges in simulation. The first one is that you need to simulate sensor data because most of your driving algorithms need sensor data as their inputs. What we do here is actually a trick which is related to how the ego vehicle processes its input data and produces its output. So typically in a simulation, the ego vehicle is reactive and it gets a new state at every time step of the simulation. So I'm going to illustrate this here with this little graphic where in red we have the ego vehicle. The green line is the output of the ego vehicle. And as the simulation starts, you'll notice that the green line is always centered at the ego vehicle and changes every frame. So let's have a quick look. So you can see that the vehicle, let's say, is getting new inputs and producing new outputs at each frame. And in this particular type of simulation, you require a new sensor input for your model at every frame if you want to use a sensor-based policy and evaluate it. But what we do, which is non-reactive ego simulation, is actually fairly simple. We restrict the input of the ego vehicle to the very first frame and hold its plan consistent for the entire output horizon. So what you'll see here is that the green trajectory, which is output by the model, it's actually the same at this very first frame as if you had a reactive simulation. But what we're going to do instead is simply hold this green trajectory constant without changing it at every frame, which means the model actually gets no new inputs. The model is just making a single prediction for a horizon of, let's say, 4 or certain number of seconds, and it will commit and run through this entire horizon without having the ability to replan. So this is how that looks. So you can see the green line doesn't always start at the center of the ego vehicle anymore, but it also doesn't shift around each frame. It's basically the same plan over the entire simulation horizon. And with this particular approach, you don't need to simulate new sensor data, because as long as you have the first sensor frame at the beginning of the sequence which you're simulating, you can run this entire simulation in a bird's eye view, just like we have visualized here, without actually inputting new sensor information into the policy. And this is a very strong assumption, because it makes it so that your policy never observes states that are not in the training data or in the original recorded data when it's being tested. So you'll always only see states that are, let's say, in the center of the lane where a human driver would be. But in exchange for this, the policy has a more challenging task, that it needs to anticipate things over a very long time horizon. It doesn't have the ability to replan if the expectation over what is going to happen in 3 or 4 seconds of the policy is wrong. It's going to be penalized with an error for making a plan that was incorrect in the long term. So this is what we do to circumvent sensor simulation. And the second challenge of simulation is actually how to simulate the background traffic. So in a typical simulation, the background traffic, which are the blue cars in this particular graphic, need to react to what the ego vehicle does. So here we show a scene where in the original recording, the car didn't come to a stop on the highway like this. So the blue cars would have kept moving straight. But if the new policy now decides to suddenly stop, you would expect the background traffic to correspondingly stop behind you. But what a non-reactive simulation would look like is basically the background ignores the ego vehicle completely, and it's going to just drive as it did in the original driving recording you have in your data set. So you can see this weird behavior of the blue vehicle driving straight through the red vehicle. And again, this is another very strong assumption, which is more or less incorrect in most situations where your policy behaves differently from a human driver. But as we'll see, this basically bypasses one of the most challenging tasks within simulation, which is how the background traffic will move, and lets you have a very lightweight behavior model of the other cars, which is just loading from their recording. So we've bypassed both sensor and traffic simulation, which are the most challenging components of running a simulation. And once you do that, you can actually use simulation-based metrics, which are, unlike displacement errors, principled in that they actually measure things that you care about when you're evaluating a driving model. So we use this bird's eye view world to calculate different simulation-based metrics, which can be related to collisions, staying on the drivable area, maintaining a safe distance from other vehicles, having enough progress, and being comfortable. I'll go into a little bit of details on each one. So you want to measure collisions by bounding box intersections in this bird's eye view space. But if you recall that we have this non-reactive simulation, there are going to be some collisions which are caused due to the background traffic not reacting to the ego vehicle. And unfortunately, since we bypassed having a proper behavior model, we need the metric to now not penalize such collisions. So we have a no collision metric, which only penalizes collisions where the ego vehicle is at fault, which is determined by the relative orientation and speeds of the two vehicles that are in the collision. So you wouldn't get a penalty if something drives into you from behind and drives through you. You have a drivable area compliance metric, which is more straightforward. If you have a HD map in your data set, you can run your simulation and see whether you drive off-road. We penalize near collisions by having a penalty for being within 1 second of a collision given the current velocity. We encourage the model to make a decent amount of progress and not be overly conservative by using a privileged planner on the exact same scenario and measuring the progress relative to what you can achieve with a simple privileged planner. And we can inspect the acceleration and jerk and make sure that the driving behavior isn't too uncomfortable. So if we go back to the scenario I showed right at the beginning, this is what you get now. With these metrics, you can clearly distinguish like these multiple facets of driving, and you observe that this particular trajectory in red is going to collide and not maintain a safe distance. This trajectory in orange is not comfortable and going into this bike lane, so not complying with the driving area. Whereas the one in green, even though it has a higher displacement error, is actually safe as per all of these different subscores that we have. And we kind of combine these into a single metric with a notion of having some penalties and a weighted average. So you have these metrics that all of the metrics lie between 0 and 1, and these penalties basically are for behavior that's not permitted, such as collision, and the trade-offs are more for behavior that is favorable but could potentially be violated in case of a complex situation. Now, this particular metric and formulation is designed to be very extensible and adaptable. So we start off with these 5 metrics, but you can incorporate more. And putting this all together, we have this final metric, which we call the PDM score. We do like a small 4-second simulation, and it correctly attributes the green trajectory in this particular scene to be the best one of the 3. So just I want to mention that based on our assumptions, like one key problem with the PDM score is that it can't be used for arbitrarily long simulations beyond a certain number of seconds. Like the task, first of all, becomes too challenging for a planner to output trajectories for like, let's say, a minute. And it also becomes like infeasible for the background traffic and ego traffic for this assumption to hold at that point. So does it work? We did a bunch of tests on privileged planners. So planners that actually take bird's eye view HD maps and bounding boxes as inputs, and used a proper closed loop simulation. So we used something called the closed loop score, which was the primary metric of a driving challenge called the New Plan Challenge from last year. In this particular score, you simulate the planner's output with the proper reactive style simulation at 10 Hertz for 15 seconds. So it doesn't use any of these assumptions that we have of non-reactiveness of the ego vehicle. And what we plot here is a scatter plot of the closed loop score, which is our sort of target metric, the gold standard for a correct evaluation, and our PDM score metric, which is plotted in red points, versus something called the open loop score, which was also a metric used in the same challenge and is primarily based on displacement errors. So this is one of the more principled open loop metrics out there so far in the literature. And we have like different shapes here for learned planners and rule-based planners. So we collected 150 different planners for this like little experiment. And what we see clearly is that the PDM score, which is the red points, kind of increases with the closed loop score. It does overestimate the closed loop score a bit, so it's not a perfect diagonal correlation, but it's much better correlated than the open loop score. And the this kind of shows that despite these simplifying assumptions, we are going somewhere with this non-reactive simulation. So besides the metrics, I still think there are quite some entry bottlenecks to doing end-to-end driving research. And this is something we also tried to handle in this project. One is that the storage requirements of doing benchmarking at a sufficient scale is often like out of reach of smaller labs. So NuPlan, for example, downloading the sensor data is 20 terabytes of storage. And we released this subset of NuPlan, which is just sampled. It's called OpenScene, where we essentially subsampled at 2 Hz, which is the typical frequency used by today's state-of-the-art methods as inputs. And we also generated some standardized train and test splits, which I talk about in a second. We made a private fixed evaluation server, so different papers can't come up with their own metrics and their own definitions of the ground truth, and this gets standardized. And basically, like, we improved the distribution of the test set a lot to deal with the problem of straight driving. So here I show the performance as per 3 of our new metrics: no collisions, drivable area compliance, and the PDM score, which is our aggregated metric I showed with the combined set of 5, where if you go to our OpenScene dataset and look at the performance of a simple straight driving with constant velocity and heading, it actually gets a quite respectable 80 PDM score already, which means that unfiltered recordings are mostly static or straight driving scenes. You also see in this plot, like, this is on the log scale, the lateral endpoint of how much you turn, and it's nearly like 80% or more that is just going straight. So we use some simple heuristics to filter out some of this data based on this constant velocity and heading baseline, and significantly improve the distribution to generate more diverse and challenging scenes. So putting this all together, we provided this interface with like a standard sensor suite. It uses this OpenScene dataset, but it can be expanded to support more datasets with camera, LiDAR, and state inputs. It looks something like what we see on the right for 1.5 second history. And we kind of re-implemented the state of the art, the best methods taken from the literature up until today on like end-to-end driving. So in the interest of time, I will not go into extremely deep details about these methods, but there are state-of-the-art approaches for new scenes, such as UniAD. This was the best paper at last year's CVPR, and ParaDrive. When evaluated on new scenes, these methods don't significantly outperform the Ego MLP, so it was not really clear whether they are making a significant improvement, given that they are very compute hungry. They use high resolution multi-view video inputs, and the training budget is extremely huge. It takes like 80 GPUs for multiple days, 5,000 GPU hours to train these models. So we re-implemented these on NAVSIM, and we are having these as our first baselines. We also took some baselines from Carla, and just as a representative, one of these methods is transfuser. These are much simpler in comparison with more lightweight 24 hours on 1 GPU style training with less output auxiliary tasks and less input resolution and sensor counts. So what does the new benchmark show us? So the first sort of good thing to know is that the UniAD and ParaDrive methods, which are the current state of the art on new scenes, are clearly better than a blind Ego MLP as per now the more principal metrics we have. So that's good. There's like quite a significant gap, and it's around almost all of the metrics, like keeping safety distances, drivable area compliance, making progress. Comfort is the one metric where all the methods kind of cap out because it's like very easy from imitation learning to learn to not have huge acceleration and jerk. Surprisingly, the transfuser method, which was more or less developed completely in Carla and simulation and has a much smaller training budget, actually gets a performance on par with these more complex UniAD and paradrive methods on this benchmark. So that's something interesting to explore as to whether like we can have much more efficient models and get good scores. And human trajectories. So if you evaluate the ground truth in the data set, this is 11% better than all sensor agents. So there's still quite some headroom to make progress in this benchmark. And the benchmark can always be made harder by extending the output horizon from 4 to 8 seconds or improving the metric definitions or adding more submetrics. So we also held a little challenge. I'm not going to go into depth on this, but we had a lot of participation, some interesting entries, and we had a lot of diverse entries. A lot of teams used foundation models, which was hinted at the introduction to this workshop. Seems that they are a thing. And we saw like a lot of variety, which was like quite exciting for us. So people didn't simply use the existing methods from NewScenes and Carla. There was a lot of diversity in the solutions to this leaderboard, and many of them perform quite competitively. I want to sort of come close to the end by giving this caveat that we do have this new benchmark and it is solving a lot of issues with previous benchmarking out there, but we still recommend complementing an evaluation on NAVSIM with a proper closed loop simulator like Carla or MetaDrive, which was just mentioned in the previous talk. This is because like the NAVSIM approach cannot do long evaluations, which are actually we have found important in our research in Carla. So we can just do like 4 or 8 second simulations, whereas these simulators can do several minutes. And we currently can't consider some infractions, like because of our definition of this non-reactive simulation, we can't penalize rear end collisions, for example. We also don't have a metric for running red lights yet. And while these things could be improved, it is going to be complementary to have evaluations on a simulator along with this benchmark in your papers or while developing your models. It is good that our particular simulation approach is much, much less compute intensive than using a simulator though. So maybe a good first step before going towards a simulator is trying out our benchmark. So yeah, that's my last slide now. The dev kit is available. You can scan this QR code or go to the link to get access to everything. Basically, we have like baselines, all the simulation implemented. It's super fast and efficient. All the data set and downloads for our like standardized splits have been simplified and made as convenient as possible to get started. And we are actively developing this framework to make it more useful in the coming months and years. So there's going to be better metrics. There's going to be more metrics. We will hopefully add support for more data sets and have more challenges in the future where we may eventually be able to resolve a lot of the issues with the non-reactive aspect of the simulation and make like faster progress by leveraging sort of the whole community. So yeah, with that, I'd like to end my talk and I'm happy to take questions. Thanks.